Okay, good morning. Today, we are starting on our discussion on energy, and that is thermochemistry, chapter 6 in the book. So I'm giving this lecture this morning because I have another class that I'm scheduled to take. So I hope you'll bear with this video recording of the lecture today. So I'll follow through the same slides that we have there on Moodle, and you can use it or go back and review it after this lecture. So energy. Let's first of all define energy. Energy is the capacity to do work and also to produce heat. Those are the two forms of energy I'd like to focus on in this lecture as we bring on this topic. And one of the first elements that we discuss in energy is the law of conservation of energy. So this is the first law of thermodynamics. And that essentially states that energy can be converted from one form to another, but can neither be created or destroyed. So you always summarize that first law into energy is neither created nor destroyed, but can be transformed from one form to another. So that's the first law of thermochemistry. We also use that as the first law of thermodynamics, the law of conservation of energy. Another way of putting it in a mathematical form, you see that the total energy content of the universe is constant. In other words, if you're determining the change in energy from the flow of energy into and out of a system, I'll talk about that as we go on, essentially zero. That is delta E, delta energy, the change in energy is zero. So those equations are going to follow on as we proceed. So some forms of energy that we need to define. First is potential energy. Potential energy, we often relate to it as a position in terms of how an object is positioned at a certain height. And that is what we determine the potential energy from. But also in chemical energy, we are looking at what we say the composition. So if you have a compound or a chemical has got chemical bonds associated with it. Those bonds carries what we call bond energy. So in total, what we have in the system is essentially chemical energy, which we regard as potential energy as a general name for that. And the other is kinetic energy. Kinetic energy is the energy of any object in motion. So I mentioned this energy already in our last chapter on the behavior of gas molecules. They are always in constant motion, and those motion can be described by their kinetic energy, which is what we gave previously, and that is half multiplied by the mass and the square of the velocity. I'll bring on the equations as we go on later. But this is just an illustration of potential energy and how that is interconverted. If you roll a sphere downhill, as in the diagram, you see that the initial position, the ball A has a higher potential energy than B. And that's, you can see from that, because of the height difference, as I mentioned, that's what the potential energy is often related to. Now, if you roll that, that energy is going to be converted to one, kinetic energy, and also energy lost as heat due to the frictional force between that ball or sphere with the surface of that hill. And once they collide, that energy is going to be transferred. So you can see here the changes in energy from potential going on to kinetic, and then this will get from potential energy and gaining kinetic to move that ball even further up. So initial state, and after A has rolled downhill, the potential energy has been converted to random motions into kinetic energy, and also the frictional heating or the frictional force between the sphere and the surface of the hill. So whatever energy that is lost here is gained plus some of the energy that is also gained or lost from within the heating that expands within that surface. Okay. Energy that we would like to dwell on for this section, and I want to focus on that in this particular lecture, is the two energy, and that is the heat energy and the work energy. Now, these two forms of energy are going to be where most of our experiences are made. Even in the laboratory class, we're going to look at the measurement of one of this. So let's just define the two. Heat energy, this is related to the change in temperature. So you see that, the difference in temperature. So that's where heat energy is obtained. And work energy is based on the change in the distance. So you're working on a force acting over distance. And you would see that force, we already discussed force when we were defining pressure. Remember, when we were defining pressure in the previous chapter, we look at force. So we're going to bring it in this section as well. So here, force multiplied by distance is work energy. Simply illustrated that if I move my trolley along the floor, that really is a work done, because the distance that you move it with, together with the force that you apply. Now, energy in general, we are going to look at this term here, the state function. It says in here, energy is a state function, whereas work and heat are not. Now, I need to illustrate this, two differences in the types of energy we're looking at. One is the energy that is state function. This is the major forms of energy that we are looking at. Those are the state function. And I'm going to mention here a few examples. For a state function, we define that is the property, we're talking about energy, that does not depend in any way on the system. Whether it's on the system's past or present. On the system past or future. Apologize for that. So state function is only dependent on the system at present. For example, the energy required to form water molecule. If you have a water molecule and you form that water molecule from the acid-base reaction, or you form the water molecule from the crystallization, the expulsion of water from a hydrate, you're forming a water molecule from there, as you've experienced in the lab. These two, although two different methods or two different paths, but the formation of water molecule, the energy that is required or expended in that will be pretty much the same. In other words, you're looking at a state function that only in the energy in the formation of water, it should be the same value, irrespective of where water was obtained from, in what chemical reaction it was obtained from. Another way of looking at state function and this work and heat. Now, work and heat are not state function, and they are regarded as path function. In other words, it depends on the path taken. For example, if you're using a different method to form water, that is the path that we're talking about. So heat and work is obtained from that particular process. Whereas the energy or internal energy itself is independent of the path taken. Another way of illustrating the state function and path function is to look at the height, elevation in a hill, or if you look at a hill, the distance from the ground level to the top of the hill is constant. Whereas if you follow the path, it doesn't matter how many paths that you take to reach the top of the hill, this elevation difference is still the same. So this is the state function. And this is the path function. Because you follow the path, that is what determines the actual path that is taken. Whereas the difference in the elevation is essentially the state function. And the path functions type of energy are work and heat. Those are the two path functions. State function, let me mention a few here. We're going to talk about internal energy, which is E. That's internal energy. And we're going to use this one here, which is the enthalpy. That's also a path function. And we're going to bring this much later on. This is another, that's free energy. That's G. And the last one I want to bring in is S. All these state functions are symbolized by a capitalized letter, and this one is entropy. All right. So these are the examples of state functions, energy state functions, and these are the path functions. So I'm going to try and dwell on this too in this first lecture and see how we can describe or define work and also heat energy. Now, when we're dealing with a chemical reaction, this is another important aspect in the chemical reaction. When, say, you have a reaction which is a combustion reaction. So let me write a combustion equation. Let's take methane plus oxygen. Now, you should know the two products when you burn hydrocarbon. The two products are carbon dioxide and water. So let's balance this out. Carbon is balanced, and you need 4. So that will be 2 water molecule. In our oxygen, you have 2 here and 2 there, so that's 4. That will be 2 oxygen. So if you carry out this reaction, what is going to happen is this. When you burn methane, you're going to actually produce heat. So when you're looking at this particular reaction is what we call a system. This is what we are, the one that we are studying or understudy. That's called a system. In the environment, say for example, all the laboratory surrounding this area is called the surrounding. Everything around the system will be the environment, will be the surrounding, sorry. Those are the environment around the system. So a system is the focus of the study, or what we are focusing on, and the surrounding is everything around that. So if you look at that combustion process, what essentially is saying is that heat is actually produced. When heat is produced in the products, that heat is gained by the surrounding. So in this case, the surrounding gains and the system lose or lost energy. So the surrounding will gain energy and the system loses energy. Let's go to the definition of the two according to the slide. Part of the universe in which we focus our attention on, that's the system, includes everything else. That's the surrounding. Everything else in the universe. That means all the surroundings in the lab, for example, or even the whole entire atmosphere around that. Now, when you look at a chemical reaction, we have this two forms of energy that I've two ways in which energy is either gained or lost, as I mentioned in the endothermic reaction. The heat flows into the system, and an exothermic reaction, the heat flows out of the system. So let's go back to this example that I gave. For the combustion of methane, you can see that heat flows out of the system, So this will be an exothermic reaction. Now, in other examples of reactions, you will have the endothermic. And endothermic is when heat is absorbed in the system, or heat flows into the system. But I'd like you to note the perspective in which this energy flow. We're going to be using signs to indicate that. If it flows out of the system, exothermic, we're going to indicate it as negative. Exothermic, that's a negative sign indicating the flow of energy, and endothermic, that'll be positive. So the sign that we bring on in terms of the quantity of energy simply indicate the direction of flow. And also I'd like to highlight this point about conservation of energy. If you have a perfect system in which the energy that flows out from the system is absorbed by the surroundings, then basically the change in energy is zero. And that's what we relate to in terms of the first law of thermodynamics. So energy gained by the surrounding must be equal to the energy gained, energy gained by the surrounding must be equal to the energy lost by the system. Now let's look at this first question. Is the freezing of water an endothermic or exothermic process? Freezing of water, you find that water will decrease in its temperature. So really, what we are seeing here, that water loses energy. It loses energy in order to drop in the temperature. So when it loses energy, that energy is given off. That means this process is exothermic because water decreases in its temperature, that indicating a loss of energy in the system. And water in this case is a system. Now let's look at the other forms of, to illustrate the two, endothermic and exothermic process. So let's classify each of this, whether it's exothermic or endothermic. All right? First one, your hand gets cold when you touch ice. That's very close to what we've just answered in the previous slide. So this one, it should be exothermic. And let's go to the next one. The ice gets warmer when you touch it. So ice is gaining energy. So that one should be endothermic. And water boils in the kettle being heated on a stove. That water is gaining energy, so it's endothermic. And water vapor condenses on a cold pipe. Water condenses in a cold pipe. That's exothermic because water is losing energy. And let's look at the last one. Ice cream melts. Ice cream melts. That's the same as the water melting. So it is endothermic. Okay, so those are the examples of heat flow, whether it's out of the system or in the system. So depending on where your bearing is, that will indicate where the sign of the energy term. So let's move on to the next set of points here. Thermodynamics is the study of energy and the interconversion of energy between the systems. Now, we've already looked at the law of conservation of energy is often regarded as the first law of thermodynamics. So we're going to bring together what the first law equation defines. And that is the internal energy that we are looking at, that is the internal energy of the system, is equal to the heat and work. That is the sum of the two. Now, what is important out of this two is that the heat and work really must carry the sign of the direction in which they occur. When you're calculating internal energy, you see that difference, or the enthalpy, the Greek sign, delta. That delta indicates the change of energy. So when you're talking about a change of energy, this is the energy between two states. And what we're saying, that the energy between two states for a internal energy, that is a state function. But you can relate the state function to the path function, and that is heat and work. So, as I mentioned earlier on, usually the state function are symbolized with a capitalized letter in the discussion of energy, and the path functions you will see symbolizes in lowercase or small letter. So here, so this is the first equation that we encounter in terms of energy. The first law of thermodynamics is that internal energy is essentially equal to, that is, a change in internal energy is equal to the heat and work done. So I'd like to focus on how we can determine these two quantities, because in general, most of the time we may not be able to measure this internal energy. However, you can do that from the work and heat. So in internal energy, the thermodynamic quantities consist of two parts. That is the number that gives the magnitude of change, and the sign which gives you the direction of flow. I've already highlighted that previously. So internal energy, the sign reflects the system's point of view. In an endothermic process, we'll look at Q being positive, as I mentioned in the example of the combustion process. In the example that we've already discussed in the melting of ice. Q is positive. In an endothermic process, Q is positive, and in the exothermic process, Q is negative. So here, if you have a system, if you have internal energy to be negative, that means the energy is gained by the surroundings, but lost by the system. So you see the direction. If you have internal energy change to be positive, that means the energy is gained or absorbed by the system, but lost from the surrounding. So the sign reflects a point of view, and in a system, when you look at work, work is negative. That if you're looking from the system's point of view. And likewise, work done on the system is negative, and work done by the system is positive. Sorry, I have to make this clear in the statement that is on the slide. So what the slide is saying is, if you are looking at the system's point of view, this is from the system. If work is done on the system, it says in there it is negative. And work done by the system, that's positive. What I'm going to illustrate is the way that we're going to use this or to guide us in the signage of this is slightly different. We're going to be looking from the surrounding. Okay, when we're looking at a work done from the system's point of view, this is how we're going to relate the sign of work energy. From the system point of view, if the work is done on the system, that work is positive, W is positive, and work done by the system, that is, if the system does work, then W is negative. To illustrate that with this pressure and volume work, which is often illustrated in a gas piston and cylinder setup. So this is a common setup that we explain the work energy based on pressure and volume work. So work, as we already looked at, is a force multiplied by distance. And you know that force is a unit of pressure. So if you bring that to the equation, we can essentially see that work is the product of pressure multiplied by the area times the height. That is a change in the height. And area multiplied by height, you see that really gives you the volume. So here's the pressure unit that I mentioned earlier. Pressure is actually force over area. And so when you apply a pressure over the cross-sectional area within that piston head, that's the amount of work done that we can indicate from, or we can obtain from that. Now, you can see here that there are two kinds of process that will take place. Assuming there is gas that is present inside the cylinder, when you apply pressure, you're compressing the gas. And if you release the pressure, essentially this should expand and revert back to its original position. So what is going on in there is essentially the two types of work that we are relating to. And that is when you move the compression work from a high volume to a less volume, a compression work, that essentially is work done on the system. And when it's work done on the system, it is going to be positive. And work done by the system is going to be a negative work. That will be related to this equation. In fact, I'm going to show you that the equation to deal with the sign from the changes based on the expansion or compression in a cylinder is essentially going to be a negative sign in order to take care of the changes in the volume. So we're going to look at that. So work done for an expansion of gas, you see that the change in volume is a positive quantity because of the increasing volume that's in expansion. Thus, delta V and W must have opposite signs. So in other words, that is the proper representation of the work done. To also bring in the sign in work energy. So when let me just recap from this, you will see that the expansion work. The work done is negative, and in the compression work, the work done is positive. And you can see that relates clearly to the change in volume. Because when you have expansion work, this delta V will be positive, and therefore your overall sign will be negative, which is what we said in there. If you have compression work, the delta V is going to be negative. So you have negative and negative multiplying out to give you a positive value. Now, work done is energy, and the unit of energy is joule. But you may see that how can you get joules from pressure, which is in atmosphere, we know, and volume in liters. So here's the conversion. To convert liter atmosphere unit to joules, that is the conversion factor. So 1 liter atmosphere is 101.3 joules. So liter atmosphere essentially is in joules. And that's interesting because remember that we look at the value of the gas constant, and the unit of gas constant that we use is liter atmosphere per mole per Kelvin. So liter atmosphere essentially is joule. Okay. Let me go into the calculation. So we go on to the next term, and that is the enthalpy. Enthalpy, as I've stated earlier on, is one of the energy that is a state function. So in a state function, the change in energy is always a indication of the state. Now, enthalpy is related to heat energy at this particular condition, and that is at constant pressure. So when you have constant pressure, and that's what we often try and maintain, in that way we can easily convert or equate the two, heat and enthalpy. Now, a change in enthalpy, as in the change of any term, is essentially heat of the project and the enthalpy of the products minus the enthalpy of the reactants. That's the two different states that are used. So let's look at an example here. We're using the combustion process, and you can see this is a very common system that we study. Combustion of a hydrocarbon, again, this one is C3H8, which is propane. If you burn it, you form carbon dioxide and water. Now notice that this is the enthalpy. This enthalpy change is what we call the enthalpy of combustion. This is actually the heat given off when you burn propane. Now, according to the equation, the enthalpy change is 2,221 kilojoules. That essentially is related to the amount of propane burned. So again, here we're going to look at the stoichiometry and use that in order to relate to the quantity of energy. For example, if you burn 1 mole of propane, that will release 2,221 kilojoules. That is essentially how we can relate this sort of data. So a question can be drawn from here. Assume that all the heat comes from the combustion of propane. Calculate the enthalpy change in which 5 grams of propane is burned in excess oxygen at constant pressure. So we are maintaining the constant pressure because that's what will give us the enthalpy change. So let's look at this example. We see that from the equation, we can relate the mole quantity and the energy quantity. So 1 mole of that will produce minus 2,221 kilojoules. That's from the chemical equation based on the stoichiometry and the amount of heat that is produced. So the question is asking in 5 grams of propane. So if you're given 5 grams of propane, what do you need to do? You're going to work out moles. The molar mass of propane, 44.094. That'll give you the number of moles. And you can multiply that so amount of heat. Okay, how do we work out the amount of heat? Let me just continue from where I stopped at. In this combustion process, we're going to work out the amount of heat that is required for 5 grams of propane. So we go to the chemical equation, and we see that from the chemical equation, 1 mole of propane, that will burn and produce this, 2,221 kilojoules of heat. And that is negative because it's an exothermic process. So in 5 grams, you will need to convert that into mole. So I haven't got that calculated, but I will just highlight it. So that's mole of propane. And this amount of moles, you're going to be multiplying that. So the amount of energy will be equal to mole of propane times minus 2,221. And that essentially is 5 over 44 times if you do that calculation, it comes up to minus 252. So we see here how we can use stoichiometry in determining the amount of enthalpy energy, that is the energy that is released for a particular compound under study. In this case, is the combustion of propane. Now, one of the reasons why this example is used is that this is often used in a colorimetric study. What is a colorimetric study? Colorimeter is a device used for measuring heat energy. So colorimeter can measure the amount of energy that is released very accurately. So here, actually this value is taken from the literature, and we are using that to determine a quantity other than 1 mole. So if you're given any mass, you can then find out the quantity of energy that is released. And also you can see that for 1 mole, which is equivalent to 44.094 grams, that is the mass of this, that will produce that. So in 5 grams, you're essentially reducing that. And you can see the amount of energy that we get. 252 kilojoules. We add in the sign because it is an exothermic process. Now let me then go on to the next slide, and that is colorimetry. Colorimetry comes from the word calorie. Calorie is a unit of energy, and that's an old unit. So colorimetry is a science of measuring the heat energy. And in order to measure the heat energy, we need this term here, and that is the heat capacity of any substances, any substance or any material that we are looking at. Now, if you have more than one material or compound that is in the system, then you need what we call heat capacity. But if it's just one single compound, one single substance, then we use the term specific. So in general, we have specific heat capacity of each of the compounds of interest. And all the chemicals or all the compounds that we are going to be looking at, you'll find that it is given a unique, specific heat capacity value. What is the specific capacity? It is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So it'll be in per gram per Celsius unit. And likewise, molar heat capacity is the energy required to raise 1 mole of substance by 1 degree Celsius. Here is talking about mass unit in gram. Here is a quantity in mole. So molar heat capacity in gram, and specific heat capacity very closely associated based on the quantity. So this is what we often conduct using colorimetry experiment, and that is mix 2 reactants and observe the temperature change that accompanies that reaction. And from the temperature change, we can then determine the quantity of heat from there. So if the reaction absorbs energy, you will see that the 2 solutions actually, or the mixture will undergo cooling. Or if it expands, or if it releases energy, then the system really is an exothermic and symbolizes by the loss of heat. So colorimeter comes in more sophisticated and even a very crude form. The most sophisticated one is what we call the bomb colorimeter. In a bomb colorimeter, that is a much more accurate device of determining the heat energy. Whereas in other devices that we're going to use in the laboratory, like in this example here, it's a homemade coffee cup colorimeter, and we still can use it effectively to measure the quantity of heat energy. So the setup has an insulated cup. That's why we use styrofoam. And you have a stirrer together with thermometer. So the most important aspect about this is to measure the differences in temperature when you mix the two solutions together. So how do we determine the heat energy? Heat is essentially related to specific heat of the material or compound we're looking at, mass, and the change in temperature. So this specific heat is often a known quantity because most of those are given in the literature, and all we need to be careful is the unit that we use for specific heat. So here is joules per Celsius per gram. Now if it's a heat capacity, remember that this will not be per gram, it'll be just joules per Celsius. That's heat capacity. And if it's molar heat capacity, it'll be joules per Celsius per mole. All right, so this is the main heat equation. Heat is equal to specific heat times mass times change in temperature. I would like you to note the two units here. Mass is grams and the change in temperature is in Celsius. So conversion of temperature to Kelvin is not necessary when you are dealing with the heat energy equation. So let's look at an example here. 100 gram of water sample at 90 is added to 100 gram of water at 10. What is the final temperature? This is an interesting problem. Let me try and solve it. Let's solve it in the on the board. So 100 gram of water sample at 90 is added to 100 gram of water sample at 10. This question here, 100 grams of water sample at 90 is added to 100 of water at 10. Find the final temperature of water. So what we can do is apply the conservation of energy, and that is Q that is lost is equal to the Q that is gained. This is the heat that we lost from the high temperature water sample, and this is the low temperature water sample. So when Q is lost from the system, Q is lost, that's negative. And the Q that is gain, that will be positive. So let's put in the equation for finding Q. So we know that Q is equal to S times mass times delta T. So this is the mass of water, which is 100 grams. So it's same thing here. So let me put in the values of specific heat. You're going to see that this is the value of specific heat of water, 4.184, times the mass of water, 100. That is the mass of water, times temperature change. Temperature change is the final temperature minus initial, T final. What was the initial? We're using the high temperature, which is 90, so we'll take 90. Okay, that should be the heat lost from the water at high temperature is going to be gained by water at low temperature. So specific heat is the same. And again, we are using the same mass times temperature change is final temperature. In this case, is going to be 10 degrees. So if you look at this equation, this is what we are going to solve. So I remember I have to put a negative sign in the heat that is lost. So let's evaluate this. You can see that these two terms are the same on both sides. They should be able to cancel out. That will cancel out. And you will end up with minus TF plus 90. That is equal to TF minus 10. Why are we using the TF on both terms? Because, you know, this, when they combine, it'll be just one single body of water, and therefore the final temperature is the same in both of them. So that'll be what final temperature is. So now let's bring the TF to the right. That'll be TF plus TF, it'll be 2TF. And take this to the left, plus 90 plus 10 will be 100. So what is TF? Will be 50. So 100 divided by 2, that gives you 50. And that is the final temperature based on that. So what we have done, we've applied the first law of energy, and that is heat gain is equal to the heat lost. And then we apply the calculation or the formula for determining heat energy. That is specific heat capacity multiplied by the mass and change in temperature. So the unique aspect about heat energy is that energy related to the change in temperature. So here is a good illustration of how you can apply the heat equation. So out of the choices there, the final temperature of water should be 50 degrees, and that's essentially how we arrive at the 50, as I've shown on the board. Now let's look at an example. Here you have a styrofoam cup with 50 grams of water at 10 degrees Celsius, and you have iron, that's 50 grams of iron at 90, and add the two together. So you add iron into water, and you're given the specific heat capacity of water and iron. Calculate the final temperature. So this follows very close to what we have just done. So I'll set it up again on the board. And that is Q gain is equal to Q lost. Q lost is negative. Q gain is positive. So if you look at this, iron starts from 90 and it's going to lose energy. So Q lost is mass of iron, specific heat capacity of iron times mass of iron times the temperature change. So again, we are working out T final minus what is initial temperature of iron is 90. And then you have the heat gain by water. It is 50 grams. So specific heat capacity of water times mass of water and temperature change of water, which is T final minus 10. So in this case, there is not a simple cancellation as we had before. So this is 4.18 times 50 TF minus 10. That is equal to 0.45 times 50 times TF minus 90. Okay, you can do some cancellation here. We can do this. But we still have to do the evaluation of the two values, the specific heat capacity values. However, what we can do is simplify that. I'm not going to go into the detail of the algebra, so I'll give you the final value. So TF comes out to 18 degrees. So we see in here the exact same setup as we did for the cooling of two water bodies. Here you have the cooling of a metal in a water body. So the final temperature comes up to be 18 Celsius. So the answer there should be C. It's between 10 and 50. So again, we are applying, sorry, I missed out the sign in this. Make sure that the sign is carried through. That is very important, because without that sign, you will see that you can simply make a serious error in the final outcome. So remember to put the signs on from the position of heat that is lost. Okay. So let's going on to the next, and that is Hess's law. Hess's law is what uses the series of energy in order to determine the overall energy. So in going from one particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. So let me see if I can explain that. You can see here the reaction given, nitrogen combining with oxygen to give you nitrogen dioxide. So that's the enthalpy of the reaction, the enthalpy change of the reaction. However, if you look at this reaction can be viewed in two steps. You have here nitrogen combining with oxygen to first form nitrogen monoxide. We see that first product. And then the subsequent reaction of this with oxygen again to form the final product, which is nitrogen dioxide. So instead of a single step, which we say as an overall reaction, here you take it in multiple steps. So multiple steps, it has the unit or energy quantity that is given from there. So here the energy is 180 kilojoules, and here is minus 112. Now you will see that in each of these steps, that first step is endothermic, that is positive, and here is exothermic. Now looking at these two steps, which are called chemical steps, you can add them up in order to give you the overall reaction. So that essentially that is what happens. You can see here that NO2 is a product, and that's already in the product. However, the NO is formed as an intermediate. We call that intermediate because it's formed in the middle of the reaction, but you don't see it in the final equation because it's essentially consumed. So that is a reaction, or what we call an intermediate in the reaction. So when you place these two reactions together and add them up, you will see that the intermediate will cancel out, or the terms that is the same on both sides cancelled out. And you add up all the terms that are the same in each side. So here there will be 2 oxygen. Nitrogen, you have nitrogen, 2 oxygen, and 2 NO2. So when you're combining these two reactions by simply adding them in the setup that they already have, the setup that you already given, then the sum of the energy will be the enthalpy of the combined reaction. So that is essentially what Hazzard's law states. The overall reaction, which is delta H1 here on top, is essentially equal to the two steps, delta H2 and delta H3, the sum of the two. So you come up to be the same. So that's the illustration of Hazzard's law. So in the diagrammatic form, you will see here that in Hazzard's law, the enthalpy change of the overall reaction from nitrogen and oxygen to nitrogen dioxide is this enthalpy change, and that essentially is this enthalpy change. So here is one single step, whereas if you take two steps, again, it gives you the same overall. And you can see that this is the path of the energy process that is taken to reach the final. Some aspects about Hazzard's law in terms of manipulating these reactions. If a reaction is reversed, then you have to change the sign. So if it was a positive sign and you reverse that, it should be negative. The magnitude of enthalpy is directly proportional to the quantities of reactants and products. So if the coefficients in a balanced equation are multiplied by an integer, the value of delta H must be multiplied. So changing the coefficients when you multiply out the value of any coefficient to bring the equations to cancel out, then you have to do the same when you're dealing with the enthalpy. So let's look at an example for that. Here's the two reactions, ammonia and ammonia decomposing to nitrogen and hydrogen, and here hydrogen combining to form water with oxygen. And note the two enthalpy of reactions here. The first one is 46, which is endothermic, and this one is exothermic. So the reaction that we are interested in is nitrogen combining with water to give you oxygen and ammonia. So we're going to apply Hazzard's law in this, and I'm going to show that on the board. So what we need to do before we start working at it is that look at what is in the products and what are those in the reactants. So here the reactants are nitrogen and water. So nitrogen is here and water is also here. So you can see that these are both products in the given equations. And okay, so let's look at oxygen. Oxygen is here and ammonia is here. So you can see that oxygen and ammonia are the reactants. So to begin with, you will need to reverse both equations. Okay, I'm going to take that step and reverse those two equations. Okay, what I'm going to do is see the setup that I have done based on what the products and the reactants are in the overall equation. As I've said, I've got these two on the right that are products, which are reactants in the given equation. And vice versa, you have the reactants which are products in the given equation. So that means I have to reverse these two equations. When you reverse the two equations, first one, the enthalpy change will be negative, and the second one, the enthalpy change is positive. Okay, that's the first modification I've done in the equation. Now the next is to try and get the, you can see that the number of moles that are there will have to be consistent with what you're going to add from here. So you're talking about 3 oxygen that is produced here. Here you see there's only 1 oxygen, so I'm going to do this. You multiply this by 3. And you're looking at 2 nitrogen and 4 ammonia in here. So here is only half, and there is 4 ammonia. So I'm going to multiply the top one by 4. Okay? So I will get this new set of equations, 2N2 plus 6H2, giving you 4NH3. And now your delta H is going to be 4 times 46, minus 46. And the second equation, you'll have 6H2O plus, 6H2O giving you 6H2 plus 3O2. And now delta H, that is enthalpy change, is going to be 3 times 484. Okay? Now if you add up these 2 equations, now you can do the additions of the 2 equations to give you your final. So hydrogen is going to cancel out, and what you're left with is 2 nitrogen, and you have 6 water, and you have 3 oxygen plus 4 ammonia. So now you have the overall equation, and what do you do with the enthalpy? So your overall enthalpy will be equal to 4 times minus 46 plus 3 into 484. Okay, I haven't got the value calculated, but you can determine that quantity of energy from the numbers, and you can get the overall enthalpy change. But however, you can see here how we apply Hazel's law, and that is, given any set of series of steps, we can manipulate that and then sum it up to give you the overall reaction. What I want to go on to, this is a summary of what we've just looked at in terms of Hess's law, work backwards from the required reaction, which what we did, using the reactants and products to decide how to manipulate the other given reactions. So in other words, you start from the final and see where the compounds are located or situated, whether it's in the reactants or products, so you can see whether you need to reverse any equations for the start, and then you can do the multiplication following on to that. Okay, so let me see the final value. All right. So actually, we got the final value given, and that is 1268 kilojoules. So that's the final value that we arrived at using this example. Now let's look at one specific form of enthalpy, and that is the enthalpy of formation. Enthalpy of formation is defined as a change in enthalpy that accompanies the formation of 1 mole of a compound from its elements in their standard states. These are very useful set of thermodynamic data or energy unit, the enthalpy of formation. For a compound, for gas at exactly 1 atmosphere, for solution concentration at 1 molar, and for pure substance, it's a liquid or solid. For an element, you will see that an element exists in the elemental state at 1 atmosphere and 25 degrees Celsius. So these are the definition of states when we are looking at different compounds. Gas is 1 atmosphere solution, 1 molar. Substance, when you're looking at pure solid or liquid. And for an element, it is in the form of whatever state they exist in 1 atmosphere and 25 degrees Celsius. So let me give you the some of the follow-on information of the enthalpy of formation. The enthalpy of formation of pure elements is 0. For example, the enthalpy of formation of potassium solid, that's an element, pure, at its pure standard state is 0. If you're looking at hydrogen or oxygen, let's say oxygen in the gaseous state at standard condition, that is 1 atmosphere, 25 degrees, is 0. It's the enthalpy of formation. And likewise, any gas, hydrogen. Notice that carbon dioxide is not a pure element. It's not. So this is certainly not 0. So when you're dealing with enthalpy of formation, only substances or elements in their standard form. Okay. We're going to look at this reaction here. I've already shown this reaction before. So we're going to illustrate Hazel's law in this reaction. So methane plus oxygen, carbon dioxide plus water. So this is another representation of Hazel's law. the enthalpy of reaction using that superscript. Superscript means the standard enthalpy. Standard enthalpy is calculated under standard condition, which is 25 degrees Celsius and 1 atmosphere pressure. So how do we determine that from a chemical equation? Let's balance this out first. It was 2, and this is 2. So when you're given any chemical reaction, to find the change in enthalpy or enthalpy change here of a reaction under standard conditions, you can use the values in the literature, and that is equal to the sum of the heat of formation of the products minus the sum, the heat of formation of the reactants. So where do we get the heat of formation values? We're going to use the literature, the data, tabulated in the textbook actually, and also you can check that online, of the enthalpy of formation of each of these quantities. So what I'm going to look at is how we use Hess's law from a given chemical reactions. So here is just one simple chemical equation, which is the combustion of methane. And how do we work out the enthalpy change? Now the enthalpy change, really using Hess's law of multiple steps, can be determined from the heat of formation of the products total minus the heat of formation of the reactants, the sum of those total. So you see that from the equation. This is the sum of the heat of formation of all the products minus that of the reactants. So now I'm going to turn to the table to get the values. So the heat of formation of carbon dioxide is 393.5 kilojoules. That's from the table. And the heat of formation of water is 285.8. It's exothermic minus, so twice that because there are 2 water molecules. And then we have the heat of formation of methane. Heat of formation of methane is 75. And the heat of formation of a pure element. You see here pure element gas form at standard condition, standard pressure of 1 atmosphere and 25 degrees Celsius is 0, so that is 0. So now we can evaluate the enthalpy change, and that's what is based on the slide that we're looking at. And if we evaluate it, it comes to minus 891 kilojoules. And that essentially is the second illustration or second approach we use in applying Hess's law. So the first one was using a multiple step reaction. Again, the same thing in here, but it's only given in a simple reactants and products. So finding the enthalpy of the overall, it is the sum of all the heat of formation of the reactants minus that of the products. Okay, we're going to finish there in our lecture today.